morning. Now that we have done a lot with the front of a diffraction, let's see how frontal diffraction patterns will look like. And as I have written here, mathematically, the frontal diffraction is mathematically complex. But experimentally, it is simple because most of the wavefronts in the near field are curved wavefronts or point sources or waves emanating from point sources which are spherical waves, and therefore you can use you can do the experiments. But the thing is to deal spherical wavefronts mathematically is somewhat complex. What we'll do here is to look at some of the simplified versions of the theory so that you can get a flavor of some devices and some concepts in frontal diffraction. In this picture, what we have shown is source point and observation point, or a point on the screen. And this SP is the line joining the two. And here we have the aperture itself. The whole thing is an aperture. And the line joining S and P says that this SP is perpendicular to the aperture plane. Perpendicular to this plane here. Look at the distances. Distance of P from O, or the center of the aperture, is H. S prime for the source point. R prime is the distance from the source point to one point Q, to a point Q on the aperture. This Q itself is at a distance R from the center of the aperture. And the distance PQ is R. The two primed quantities are on the source side and unprimed quantities on the observation side. Therefore, PQS, the distance travelled by a light ray, this distance, P to Q or S to Q, is R plus R prime. And that R plus R prime from Pythagoras theorem. We can see this one, and we simplify, get something else. Here we have taken that's not accurate. Now, to start with, what we are going to do is to illustrate the concept of frontal sound. Now see these dotted lines, all these dotted circles. What it does is to divide the aperture into what is called Fresnel zones. And the radii of these guys, okay, let's say this is R1, then you have R2, then you have R3, etc. The radii are such that R plus R prime differs from by lambda by 2 from one boundary to the next boundary. Let's say we have this as one boundary and this as the other one in on the aperture. Now this is your source point, this is your observation point, this is your observation point, and let's say there are two lines. This ray, which is here, and this. Now here we have R1, here we have from this under R2. This is let's say R1 prime, R1, R2 prime. What it says is the difference in R, or the radii R1 and R2 are chosen such that R2 prime plus R2 minus R1 plus R1 prime. It's a physical division, let's say. You can divide it saying that with the condition that this is your the difference R plus in R plus R prime is lambda by 2 from one boundary to the other. From this boundary here to this boundary here, it is R plus R prime differs by lambda by 2. And these regions, if you divide it, you call it Fresnel cells. And you can see that the successive radii is R1 lambda L, R2 square root of 2 lambda L, etc. If you have an nth zone, then that becomes n lambda. You find it from this expression for the two radii. Where this L is basically this is L inverse. Or L equals 1 by H plus 1 by H prime inverse. Let's say if Rn is inner radius of n plus 1 cell sum. Sorry, inner radius of n plus 1 cell, or in other words, that's the outer radius of nth cell. They both are going to be the same. Then Rn plus 1 is outer radius of n plus 1 cell. This is Rn, the outer diameter, and this is Rn plus 1. Then the difference in area is actually pi r1 square. That is for an arbitrary n. If you have r2 square minus pi r1 square, pi r2 square minus pi r1 square, you should still get pi r1, and which is independent of n. Which means that in such a situation, areas of all zones, to get a feeling for for the dimensions of this zones. Let's say you have taken h equals h prime equals 50 centimeter. This one here for a wavelength of 600 nanometers. Then R1, the radius of first zone, is square root of lambda L, where L is 1 by 50 plus 1 by 50 to the power minus. If you do that, it is 400 microns or 0.4 millimeters. If you have something like that, if you have 100 zones, the total dimension is about 4 millimeters. This means that these zones are extremely small, of the order of microns. Now, now that we have defined zones, what are these zones? We have the aperture. This is your aperture. That aperture is divided into many zones under the conditions stated above. That was the difference in the path length from one zone to the other is equal to lambda by 2. That is the condition for making these zones. Now, let's say this is zone 1, zone 2, zone 3. And what you are trying to do is to try and find the field at the point P. And therefore, the contributions or the total field at P has contributions from all over all zones, U1, U2, U3, etc. But they have a path difference of lambda by 2, which corresponds to phase difference of pi. There is a 180-degree phase difference between these two zones. And therefore, the total field, according to maybe what we can say the superposition principle, this is a sort of superposition principle. U1, the modulus of U1, because it's 180 out of phase, U minus U2 plus U1, U3 minus U4 and so on. That gives you the total field at the point P. Then there are some interesting properties. Suppose there are n zones. They are equal. And therefore the contributions from each zone, they have equal area. And therefore the contributions from each zone with a uniform illumination will be the same. That means U1 minus U2 plus U3 minus U4 plus X3. Then it depends on whether this UN, if n is even, there are equal number of minus and plus signs in the summation, and therefore the value of UP will become 0. The field will be 0 at the point P. Then if n is odd, all the contributions except one of them will remain, and therefore it will be U1 if n is odd. And if obligatory factor and radial distance factor in the Kronecker formula are also considered, then UN decreases slowly with it, which means U1 may be slightly higher than UN. It depends on the value of UN. Earlier we said they are approximately equal. Ideally it should be, but there are some obligatory factors, like if we have several zones, one, two, and then you have N. Here you have source point. It is almost like parallel or to the central line for the first zone. But when it comes to the nth zone, it's going to be very steep, and therefore in that case we may have to take into account, as you increase the value of n, you may have to take into account the obligatory factor. Then UN decreases slowly with n. Therefore, UP becomes U1. Instead of U1, U1. How do you do it? You take. Okay, this is your actual equation, U1, U2, U3, all moduli added together. Just divide U1 into U1 divided by 2 plus U1 divided by 2. Then you have U2, U3 divided by 2, U3 divided by 2. Summation that should give you U3 and so on. Let's say I'm doing it for all odd n's. And here I have shown some brackets and quantity inside the brackets, because since U1 is equal to U3 and also equal to U2 or 2, and therefore you can the quantities inside the brackets you can select. If the decrease in UN with n is okay, n is slow. In the sense, here we are comparing the second with the first, second, and third. Here we are comparing third, fourth, and fifth. Which means we are comparing only the adjacent or very close field zones, and therefore inside the brackets it could be very nearly zero. These things are zeros, and the other factor is UN tends to zero as enters, and therefore value of the point is U1 over 2. Okay, that's what we have written here. As n tends to infinity, the field at the point P becomes U1 by 1, or intensity, half of the intensity, half of the field amplitude that's going through the first convection. Now, with this concept, we can make devices for songs. What we had described in the Fresnel zones was it is a concept. It's not a device. It's not a doesn't have a physical origin, but we can do that. We can use that division of funnel zones. Okay, these are zones of equal area, and to make something called zone pins. Now we can calculate what the radius of the first zone is. We can calculate the radius of the second zone. We can calculate the radius of the third zone, and also first, second, third, and also what is it? Okay, you can calculate, and also the thickness. You know exactly what it is. But then we can also make them. Make a device in such a way that the second zone, this dark zone here, shown as dark zone here, then the fourth, then the sixth, eighth, or vice versa. You can physically block them, and if you block them, the actual equation UP equals modulus U1 minus modulus U2. This minus sign, as I said, is due to the 180-degree phase difference. Then you have U plus U3, contributions from the third zone, contribution from the fourth zone, etc. Now if we block the second, then the fourth, then the sixth, block all this. This is minus. Okay. If you block all this, whatever is left is U1, U3, U4, etc. This advantage of this quantities here is they are in phase. These contributions are in phase. Therefore, they add up. In the past, if you don't physically mask them, UP can be 0 if n is even, and UP can be U1 if n is odd. Isn't that what we have seen? And if you take into account the obligatory factor, etc., you get this value as U. That is interesting. If you block the Fresnel zones, alternate Fresnel zones, then the fields are in phase. Means the resultant field on the screen will never go to 0. It will always be greater than 0. I mean, greater than 0 in the sense it is never 0. It doesn't cancel out. Because it's a field amplitude, it can be positive and negative, but as an amplitude. But the contributions, U1, U2, U3, will always add up. And such an aperture is called zone. What does a zone plate do? We have a point here, and the light is coming out of that point, and that point can be reproduced on the other side, or these Fresnel sound plates can be used as lenses, converging lenses. It acts very much like a lens. What does a lens, positive lens, do? Concentrating energy and the equivalent focal length is L equals R1 square over lambda, which also means it is very chromatic. It depends on lambda directly. The focal length of the lens depends directly or is inversely proportional to lambda, which means we can define the focal length and also a sound plate for a particular wavelength. Or the sound plates or Fresnel lenses are wavelength sensitive. That's why it is called chromatic, very chromatic lens. But still it finds a large number of uses in many fields of optics, especially in the UV and X-ray, especially in the X-ray. Okay. That's about the introduction to Fresnel diffraction.